Hello everyone! In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will begin to understand or describe quarks. So, in the last video we began to sort of dissect the standard model of elementary particle physics, and in particular we distinguished between the fermions or fermionic properties and bosons, okay? And we said that the fundamental thing to recall about the difference between fermions and bosons is that fermions cannot occupy the same physical state. That is, they obey the Pauli exclusion principle, whereas bosons can. Our typical example for fermions included basically everything we've ever seen up to this point, including electrons, protons, and neutrons, whereas bosons included photons as a sort of example. So, all right, protons and neutrons are not fundamental particles. They are not the particles that are at our most elementary level of physics. As it turns out, they are composite and composed of fundamental particles. The fundamental particles that compose the protons and neutrons that we're familiar with are known as quarks. Named in 1964 after a poem, 3 Quarks for Mr. Mork. The quark is sort of, as a name, stems from an era of particle physics where you could get people to fund things regardless of what you named it, and the physicists at that time had a little fun with it. They have since discovered that it is much easier to get non-physicists to fund things if you name them inspirational things like dark energy or dark matter, but at that time they were having a little fun. And quarks, or the elementary particles that make up virtually all of the nucleons that we consider to be fundamental. There are 6 flavors of quarks. That is a technical term that you need to know. So quarks come in 6 types, known as flavors. No, they're not actually flavored one thing or another. And those 6 types are up, down, charm, strange, and top and bottom. And that is in rough order of importance and discovery. One thing to know is that of these 6 flavors of quarks, these are the only 2 that we ever see on a regular basis. The rest have been discovered in particle physics experiments and in other circumstances. Fun fact is that top and bottom, which are already silly enough, were actually changed from their original flavors. They were known as truth and beauty when they were originally discovered, which is probably my favorite fact about the quarks. So, all quarks are elementary. They are all fermions, so individual quarks cannot occupy the same physical state at the same place in the same time. And they interact via all 4 fundamental forces. So quarks can interact via the electromagnetic force, via the weak force, or the weak interaction, via the strong interaction, and they have mass, so via the gravitational interaction. Up and down are by far the most stable due to the fact that they have significantly lower mass than the rest of them. Unstable quarks can decay or transmute into other things, which we will get to a little bit later on. So charm, strange, charm, strange, top and bottom quarks all decay very quickly or can only be found in either cosmic rays, which are sort of natural particle accelerator experiments, very high energy particles coming from space, or in the laboratory in a particle accelerator. Now, fun fact, they all have what is known as fractional charge. And there's sort of a funny thing here where we discovered that the electron and the proton had sort of these individual quantized charges, and we assumed that those were the smallest, most elementary amount of charge. Therefore, we called that amount of charge the elementary charge. As it turns out, quarks have fractions of the elementary charge. So up quarks, charm quarks, and top quarks all have plus 2/3 of the elementary charge. Down quarks, strange quarks, and bottom quarks all have minus 1/3 of the elementary charge. We will see how this plays out in a bit. It's worth noting that experimentally you will never see a fractional charge. So there is a deep sense in which we've never seen this because, as it turns out, quarks will always come grouped together in one form or another. Last comment here, we group the quarks into what are known as generations. These generations are simply sort of the level of mass and energy, that they interact at. Couple of other sort of mathematically related things, but it's just useful to know that this categorization up and down are first generation quarks, charm and strange are second generation, and top and bottom are third generation. One final comment about quarks. Quarks, for every quark, there is an antiquark. So these are first antimatter particles, and it's worth noting that for every example of particle we have here, there will be an antimatter particle, at least for all the fermions. And as a result, you should know that all of the antiquarks have identical rest mass to the quarks. So the mass of the up and the down quarks are exactly equal, respectively, to the up or the anti-up and the anti-down quarks. But they have exactly opposite charge and quantum numbers. So every up quark has a plus 2/3 elementary charge. Every anti-up has a minus 2/3 elementary charge. Charge is one of an example of a quantum number, which we haven't discussed yet, but there are others. So there are other quantum numbers. You can think of those as other quantum properties in addition to charge. Charge is just the only one we've seen so far. So they have opposite charge in addition to the other opposite quantum numbers that exist. Antiquarks and antimatter in general will take on a larger importance when we begin to sort of predict the result of fundamental interactions and reactions between different particles.